In this lecture, we'll discuss minimum spanning tree. A minimum spanning tree is actually, by definition, it's very simple. The definition is that it's just a subgraph. Remember this word. This is just a subgraph, and it's just a subgraph. And secondly, this subgraph of the original graph, it contains all the vertices. Okay, so which means that if we look at this graph down there, it has four vertices. So a minimum spanning tree would be a subgraph of this original graph, which contains all the vertices, which means that we can remove a few edges from this specific graph. And which edges to remove is the condition that it still remains a tree. Okay. By definition of a tree, it means that from every vertex there is a unique path to another vertex, and the graph should be connected. Okay, so overall, the definition means that we need to remove a few edges from this graph to make this graph to keep it connected, while there should be a unique path from each vertex to any other vertex. So it would be, by definition, it would be a tree. So converting a graph into a tree is actually called a spanning tree, and this that tree should contain all the vertices in the original graph. So that's the definition of it, of the minimum spanning of the spanning tree. Then if you just look at the idea here is that if I have two vertices, I need only one edge to connect them. If I have three vertices, then I need two edges to connect these three vertices. So this is a connected graph. For four vertices, I need at least, or at most, in fact, at most three edges to connect four vertices. It means that whenever I have n vertices, I need n minus 1 edges to create a spanning tree, to keep the graph connected. So if I just add one edge to these n minus 1 edges, that would definitely be a redundant edge. That is not adding any connectivity or connectedness to the graph. So it means that I need to keep only those edges that keep the graph connected, and I need to remove the remaining edges that I do not need or do not require to, or the edge I need to remove the edges that do not add any benefit to the graph. So that's the spanning tree. Okay, so which means in general in the algorithm I need to pick uh, n minus 1 edges from the set of edges that make this graph a connected tree. So let's see. Let's see a few more details of this spanning tree. The first thing is that a spanning tree is not necessarily unique, which means that a graph may have multiple spanning trees. Okay, so we'll see a few examples now. So this is a graph. So some spanning trees could be this, like this one. I have picked three edges in this zigzag shape. So now this graph is connected, and it's a tree. Okay. Similarly, I could pick these three edges, and it still is a spanning tree. Okay. So there are many ways that I can actually pick edges to create spanning trees. In fact, I'll show you another slide. Like, for example, in this specific graph, what I have is that I have um, 16 vertices, or these 16 vertices that are connected via 35 edges. So these 35 edges may represent anything that their relationship between these 16 vertices. But if I just need to pick the minimum number of edges that are required to keep this graph connected, whereas removing the redundant edges that are not adding any connectedness to the graph, then I would need only 16 minus 1, that is 15 edges out of these 35 edges. So those 15 edges are actually these red ones, which means I have ignored all these gray edges, and still this graph is connected. And if I pick any one of these vertices as a root node, then the remaining nodes, if I make this graph somewhat directed, then it would be a tree. because a tree actually has a hierarchical relationship. So I need to define that hierarchy as well. But if I just maybe pick this one node as a root, and I just hang all the remaining vertices from this root vertex, then this would be a tree, because from this root node, starting from this root node, I would have only a unique path from this node to every other node. So that would be a tree. So like I could have picked these other 15 edges as well. So in any graph, there can be multiple spanning trees, but they, now we are moving towards another definition, that if I have I can have multiple spanning trees, then which spanning tree is of most interest to me. So we'll see in a few slides that that's a very interesting concept, and there are many applications of this spanning tree from a graph. So let's see. For example, for this the graph that we already saw in the previous slides, this specific graph is so generic, or so general in the form that I can pick a number of different spanning trees. So there are 16 different possibilities. So how I came up with these 16 possibilities is that if you just go naively to reach these 16 possibilities, is that I have these six edges in this graph. I need to choose three edges at random. So I would pick three out of six edges. So that's 6 C3, which is actually 20 different combinations. So I can have 20 different combinations of three edges. Now, out of these 20, I need to delete those combinations that actually create a redundancy in the graph. So, for example, if I see this combination of three edges, this creates a redundancy, because this fourth node is not connected, whereas these three vertices, they actually are connected via three edges, where one of the edges is redundant. So I would remove such possibilities that create loops. So there are four possibilities that create loop in this specific graph. So I would actually just ignore those four possibilities. Then the remaining 16 are the ones in which I have not created any redundancy in the graph. So there are these 16 are the remaining possible combinations of the edges, of the three edges out of six edges that make a spanning tree. Okay, so now out of these 16 spanning trees, which spanning trees are of more interest to me and which are of less interest to me? For this definition, I need to add a few more points into this specific graph. So in this definition of a spanning tree. So in general, what we have seen so far is that I have actually defined a graph, and then I have picked n minus 1 edges to make it a spanning tree. But what additional I could have is that I can have weight on the edges. Okay, so by weight, what I mean that in this graph, if now I have a cost of using this edge in the graph, then I can actually add up the cost of all the edges that actually are part of the spanning tree to make it to actually know the cost of the entire spanning tree. So if I pick these red edges, they form this spanning tree. 4 is the root of the tree. So for this spanning tree, I would just add up the costs of all these edges that I've used. So that cost is actually 20. So that is 5 plus 2 plus 3 plus 4 plus 4 plus 2. So that's 20. Whereas for the second possibility of this same graph, this is another spanning tree that is rooted at node 7. For this specific spanning tree, what I have is that the cost is now 14. It is actually 2 plus 2, 4, 4 plus 2, 6 plus 3, 9, 9 plus 1, 10, 10 plus 4, 14. So that's the 14 cost. So the cost of the previous spanning tree was 20, and the cost of this new spanning tree is 14. So now I have a measure that which spanning tree is better than the other one. So maybe if I'm interested in reducing the cost of the edges, then this 14 is a better tree. Okay, so in this definition, now I have added the word minimum spanning tree. So this minimum actually relates to the cost of the edges that I've used to create this specific spanning tree. So now I am interested in finding the spanning tree that gives me the lowest cost. Okay, so for that I need to have a weighted graph. Okay, so that's the actually main idea of the spanning trees, that I would actually try to find a minimum spanning tree instead of just finding all possible spanning trees. So now I have a concept of minimum spanning trees. So let's see uh, if we have only one minimum spanning tree in a graph or not. So the answer to this is that no, there can be multiple spanning trees with the same cost. So it's not necessary that the cost of one spanning tree should always be different than the other spanning tree. There can be multiple spanning trees with the same cost as well, which means, or which takes me to the point that I would be only interested in finding any one of those spanning trees. I'm not interested to find all these minimum spanning trees. I'm just interested in finding the any of the minimum spanning trees, any one of the minimum spanning trees. Um, so now what? At sometimes another thing that comes up is that sometimes we do not have a connected graph. There are some portions of the graph that are not connected to the other portions of the graph, which means that in that case, I might not, in fact, it would not be possible to pick n minus 1 edges that keep the graph connected because the original graph was not connected. It means that in that case, I would pick actually not just one spanning tree, I would pick a spanning tree for each connected portion of the graph. Okay, so I would actually make, if there are n subparts of the graph, so these parts are connected among themselves, but they are not connected with each other, then I need to pick n different spanning trees or n different subgraphs. And of course, the there are applications where I'm interested in finding the all possible spanning trees that actually, or maybe all possible minimum spanning trees, uh, which which are not actually connecting the entire graph, but they are the minimum spanning trees of a subpart of the graph, and having all of them together makes a spanning forest. Okay, so for this graph, for example, this is one connected portion, this is another connected portion, and this is the third connected portion. And then what I would have is that I would have three different spanning trees, and I can actually keep these three as a knowledge, and then I can use them to maybe just add one new vertex, one new edge to connect these two parts, and then add another another edge to connect the third part as well. So I would actually know from this solution that now I need to add which two edges to connect the entire graph. Maybe that's an application. If it's a road network, if it's a computer network, then I would actually just reduce my cost to adding two more edges in this entire graph to just uh, come up with the entire connected graph. Okay, so there is another concept, spanning forest. And then of course the edges are the edges that are used to that actually give me the minimum cost. I'm more interested in finding those edges to create a spanning tree. So I would be interested in finding minimum spanning forest as well. Then now after this entire definitions and the and some formulas, now it's time to discuss some applications for which we are going to find these spanning trees. So the first application, these two are very similar applications. That, for example, this is a board on which different devices are connected, different elements are connected. What I need is that there is a power supply, and I want to connect all these devices with the power supply, because all these devices need electricity to run. So what I need is to lay down the wires on this board that actually send a current to all parts of the board, but there is no redundancy. Okay, so in that case, I would need to find a spanning tree to connect all these. Maybe this is one vertex, this is another vertex, then this is another vertex. All these elements, if I need to connect them from this power supply, maybe I need just to find the edges that are not redundant. And maybe if this edge is of a higher cost, then I would just connect this element with the second element. So in having a smaller circuit wire is better than having a longer one. So in this way, if I find a minimum spanning tree, I would reduce the cost of making this chip, this board. And then similarly for a building, maybe if I just want to lay down the electric electricity wiring in this building, I would not like to have, if there are, maybe this is one room in the building, this is another room, then there is another room. And maybe here somewhere is a generator that's generating electricity or the power supply. I do not want to lay down separate wires to each room. This would be too costly a solution. So what I would like to have is that I might want to maybe connect, maybe I would like to connect, instead of connecting directly, I would like to have one wire to first room, and then from this room I would like to have a smaller wire to the second room, and then I would like to have another wire that gives me the least cost of laying down the wires in this building. So that would be definitely a minimum spanning tree from the graph of all the rooms in the building. So connecting the rooms via smaller length wires is a viable solution, instead of laying down a longer wire to each room separately. Okay, after this application, the another application that actually laid down the foundation was by Czech mathematician Otakar Barufka. So this Barufka algorithm to find a minimum spanning tree was the first algorithm, and it was invented in 1926, and it was actually for the same purpose, to design electricity grid in the city of Moravia. Okay, so that's the application of the uh, minimum spanning tree. Similarly, we can have other applications as well. In fact, you should think of a few more applications. There are many other applications, but you can think of a few applications before going into the other algorithms. So um, then this is another application, that if we have different offices of maybe of an organization in different parts of the city, then what we can have is that we need to connect these offices via our local area network. So in that case, what we would do is that we would actually try to use the minimum number of resources, or minimum cost of the resources. Okay, so in that case, we can still find a minimum spanning tree to connect all these locations, or all these areas in the network. So that would be something like this, and that's the result of a minimum spanning tree to connect these offices via a network. So that's the idea of minimum spanning tree. In the next video, we'll discuss a few algorithms to find a minimum spanning tree from different from a graph.